In this problem, we want to calculate the cell potential for the cell. We're given the standard cell potential is 0.74 volts, and we're given lots of concentrations. So we're going to use the Nernst equation. Cell potential is equal to the standard cell potential minus 0.0592 over N times the log of Q. Well, Q is products divided by reactants. So we have Mn2 plus. We're going to omit water because it's a liquid. We omit liquids and solids from the Q expression. So products raised to their powers divided by reactants raised to their powers. And we're given all of the values for concentrations in the problem. We're given the standard is 0.74. N is the number of moles of electrons transferred. Well, if we go back to this half reaction, which we used in the previous problem, you'll notice in the overall equation there's 5 iron ions. And so that means this half reaction is multiplied by 5. So the number of moles of electrons is 5 based on the balanced equation. So we have all of the values. Now it's just a matter of plugging in the values in the appropriate places and solving for the cell potential. So we have the cell potential equal to 0.74 minus 0.0592. N is 5. And then the log of Q. Plug in all of the concentrations here. And make sure you raise those concentrations to the appropriate powers. And we can solve for the cell potential. So I'll let you do that in your own calculator, but the cell potential should come out to positive 0.42 volts. The nickel-lead voltaic cell undergoes this reaction. We're given the standard cell potential, we're given the cell potential, and we're asked to find the concentration of nickel. So again, the Nernst equation Q is products divided by reactants. We're going to omit solids. So when we omit the solids, Q looks like this. Plug in our numbers. The cell potential is 0.183. The standard cell potential is 0.124. N, the number of moles of electrons. Well, we're going from nickel to Ni2 plus, and so that is going to require 2 moles of electrons times the log of nickel, which is what we're looking for, over lead. Concentration of lead is 1. This will simplify to negative 2.0 equals a log of Ni2 plus. To get rid of log, use the 10 to the x function on your calculator. That will get rid of log. So when I take 10 to the negative 2.0, I get the concentration of nickel equal to 10 to the negative 2 molar. We've looked at the relationship between Gibbs free energy and the equilibrium constant earlier with thermodynamics, and the relationship looks like this. There's also a relationship between delta G and the standard cell potential for a redox reaction, and that relationship looks like this. N is the number of electrons transferred, F is the Faraday constant. We can combine these two relationships, and we can relate the standard cell potential to the equilibrium constant K. So the standard cell potential equals 2.303 RT log K divided by NF. Or, another way to write this is log of K equals NF E cell divided by 2.303 RT. For a spontaneous reaction, delta G is negative and E is positive. So here's how we tell whether a reaction will be spontaneous or not. Let's look at this problem. Calculate delta G and K for this chemical reaction. First off, we need to get the half reactions that are occurring. And the half reactions, again, go back to the electromotive series as you're trying to determine these half reactions, but here's one of them. Standard cell potential is negative 0.74 volts. Now I did multiply the half reaction by 2, but I did not multiply the standard cell potential by 2. It's still negative 0.74, and again, go back to the electromotive series and you'll see where I'm getting these numbers. And then my other half reaction looks like this. This half reaction was multiplied by 3, but the standard cell potential was not. Negative 0.15. When I add these together, the overall reaction has a standard cell potential of negative 0.89 volts. Since the standard cell potential is negative, this is a non-spontaneous reaction. Calculate delta G. Well, delta G is equal to negative NF E cell. N is the number of moles of electrons, 6. F, Faraday constant. And E cell is negative 0.89 volts. So delta G comes out to positive 520,000 joules. Delta G is positive. The standard cell potential is negative. They're always opposites. Okay, so there's delta G. Also calculate K for this reaction. Well, I know the log of K is equal to NF E cell over 2.303 RT. So N, 6 moles of electrons. F, the Faraday constant. And E is negative 0.89 volts. divided by 2.303. R is 8.314. And temperature is 298 Kelvin. So we get the log of K equal to -90. So K, the equilibrium constant, 1 times 10 to the -90th. No units for K.